Let us read this question properly. Two bars or blocks of masses m1 and m2. So this is the block of mass m1. Let's say this is the block of mass m2. I'll denote the masses right now. Let's say this is m1, this is m2. So these are the two blocks that are connected by a non-deformed light spring. So this spring is massless. So when they say light, we have to assume that it is massless, and it is on the rest on a horizontal plane surface. So let me also draw the horizontal plane surface. Let us assume that this is the surface on which it is resting. So now the coefficient of friction between the surfaces of contact, which is like between m1 and the surface of contact, horizontal surface, and m2 and the surface of contact, the coefficient of friction everywhere happens to be equal to mu. So this is the coefficient of friction, mu. Alright. So what is the minimum constant force F? They have asked. That needs to be applied to the bar of mass m1 in order to shift the other bar. Okay. So this is the force F that we have to apply on the block m1 in order to shift the block m2. Alright. So here there is a very common mistake that can happen. The mistake is to solve this particular question using only dynamics. Now why is that a mistake? So we can do the following. See, this is the block of mass m1. Let us say this block shifts by a distance x. Let us say this was the original position of the block, and now the block, okay, in the original position the block is of course connected via a spring to the block of mass m2. Now if we compress this and let us say m2 is just about to move, when m2 is just about to move, it is understood that the friction force acting on m2 is nothing but mu m2g. So the m2 block is being pushed towards the right, and the friction force that will be acting on m2 will be mu m2g towards the left, and the spring force of compression that will act on m2 as a pushing force towards the right has to be also equal to mu m2g. So that much is understood. Now m1 is compressed by, let us say, x distance. So let us say this is the x distance by which m1 is compressed. So it is very easy to say that currently m1 has moved the distance x. So there will be a force, let us say kx, acting because of the spring. There will be a force of friction which is mu m1g, and kx happens to be equal to mu m2g. Therefore the applied force is going to be equal to mu m1g plus mu m2g. Alright. So this is considering the equilibrium of the mass m1, but here we fail to realize that if we do this question in this particular manner via equating these three forces as F, Kx and mu mg, then we are forgetting that some work is also done in compressing the spring, and it may not be necessarily true that even though the block is moving very slowly, the energy that is stored in the spring is not taken into consideration while pushing on m2 basically. So this is not the correct way to solve this question. We cannot solve this question using only dynamics. So we are applying a minimum constant force. Alright. So minimum constant force is being applied. Now at the moment when m2 just starts moving, at that time what is going to happen is m1 and m2 are going to be both stationary. Instantaneously both of them will be stationary. So this is m1, let us say. This is the spring. Now let's assume that the spring is compressed by x compression. So this is m1 and this is m2. And this is the force F that is being applied. Alright. So this is the force Kx. Okay. So now the thing is this. The spring has stored potential energy. So not only the Kx force of the spring is pushing on both the masses, but the spring also has stored potential energy. And the force F has done some work in order to store that much amount of potential energy into the spring basically. So the net work done by the force is going to be F x And the net work done by friction on M1 is going to be equal to minus mu M1 Gx. Alright. And since the net change in kinetic energy is 0, then this particular thing will get stored as potential energy of the spring, or rather the work done by the spring force is going to be equal to minus half k x square. This is the important point to realize over here. This is extremely crucial. So from this particular equation we get the network to be 0, because 0 is the change in kinetic energy, and using the work kinetic energy theorem we know that the network done by all forces is going to be equal to the change in kinetic energy of the system, and here the kinetic energy of the system is 0. So why is this particular equation true and why is this particular equation not true? The reason is because the force F is acting towards the right hand side and Kx and mu mg are acting towards the left hand side. So we cannot write that this is in equilibrium because the force F is still moving the particular block. So we cannot write that this is in equilibrium instantaneously because motion is still happening. That's why this particular method of dynamics is not suitable, or it is inappropriate basically. So now in this particular way we can find out the force F. Force F is equal to mu m1g plus half kx, and kx is definitely being used to move this mass, so kx is going to be equal to mu m2g. So we can write down this is mu m1g plus half mu m2g. That is going to be the correct answer, and here this energy method has to be employed and the dynamics method is not exactly correct. So this is something to be noted.